Right, we are 2 minutes over the submit the code as well. And there was a question about do I insist that the output should be in LaTeX? You know, I was just telling, what's your name?
Jacob.
Jacob. I was just telling Jacob, there's no need for you to do it in LaTeX. That said, you would find it much easier if you, not for this one, but for forthcoming assignments, if you write the equations in LaTeX. I have tried to write equations in Microsoft Word. I end up just writing it in LaTeX and pasting them as images. So I really don't want to push you to learning LaTeX, but there's no harm if you do. In fact, I would appreciate it because you would appreciate it. You would probably spend less time writing math that way. Again, no compulsion there though. Do what works. I do insist on PDFs. I don't want to see other formats. The report has to be a PDF. Was that another question that you had asked?
There was, but
you forgot.
Oh, I was asking if we could bring the homework early.
Oh, right. So this is not an exam. So please come use the office hours. Come talk to us. We'll be more than happy to help you out. If you feel like you just want to, verify things, sure, come talk to us. There's no reason not to. In fact, that's what we are here for. In fact, the way I think of these homeworks is I don't think of them as exams or ways to torture you as much as it may seem like that. I prefer to think of homework as an opportunity for you to learn something beyond what I can teach in class. Learn by doing. Because the subject is so huge that I feel like I'm robbing you of an opportunity if I don't, somehow push you to do more. And homeworks are my sneaky backdoor way of getting more content in. And in fact, the other point of the homework is the lectures only tell you what things are. In the homework, you will do things and kind of play with ideas and figure out answers by yourselves. So, please talk to us, talk to each other. Again, of course, you have to write your code and write your reports by yourself, but that doesn't stop you from talking to anyone that you want. Do cite your sources. Other questions about homeworks? All right, so we are in the middle of the decision tree learning algorithm, and I'm going to continue from there. And in the last lecture, somewhere towards the end, we were looking at this recursive algorithm, the ID3 algorithm, which is sort of a basis for a lot of decision tree learning algorithms out there. And it is a recursive algorithm. The goal is I'm just going to spend a couple of minutes reminding you of what this is, and we can pick up from where we stopped last class. So the algorithm is recursive, and the input to this function is a set of examples, a set of labeled examples. And there is one column in the data, one attribute that is marked as special, that's the label, that's the one that you want to predict. And then you're also given a list of attributes. These are just, think of this as parameters to the function. And the base case for this recursion is if all examples in this collection that are given to you right now have the same label, then you just say that you create a leaf node and with that label. Otherwise, you have to construct a tree. To construct the tree, you pick a root. You pick a root attribute that best classifies this collection of examples you have, and then you move down. For every possible value that the attribute can take, so you create a root node, and for every possible value it can take, you're given a collection of examples, right? You take the subset of that, where this particular attribute A has the value B. And now you have a collection of examples and you have to build a tree. So it looks exactly like the original problem you had. The original problem was you have a collection of examples, you have to build a tree. Now you have a subset of examples and you have to build a tree. So you just make a recursive call. That's this thing here. Oh. That's this bit here. You have a collection of examples, you just make a recursive call. If the collection of examples is empty, you don't, so there is no training example where the attribute A takes value B. Then you have no data to make any reasonable estimate. So you make the most reasonable estimate, namely the most frequent label in the original collection, in this collection here. Right? So in terms of the mechanics of this algorithm, the only thing that remains to be specified is what is this best attribute? How do you define best? So before we go ahead with that, are there any questions about the nature of this algorithm? You will be implementing this for your homework, by the way. So if you don't have questions now, you can implement it and then you will come across questions. No, that's the way of learning, right?
So do we take the common value of S, or do we go like, say, one super level of SD or something like that?
So you want, yeah, okay, you're talking about this situation, right?
Yeah.
This is the easiest thing to do. You can be more clever there. You could do other things, but in some sense this is the most trivial thing to do. Given the input to this program, this is all you have. You don't have the parent. If you want to tweak this, yeah, sure, you could try other things, but this might be really the simplest thing that you can do with this situation here. But yeah, you could be more clever. Yes?
With that same, talking about that same S of B, if S of B is empty, why do we even have B? Is that sort of like a green triangle in the example?
Right, yes, exactly. So the assumption here is that there is, that's why I passed the attributes and as a parameter here. There is this global list out there of all attributes and all possible value each one of them can take. And it just so happens that this particular value does not manifest itself here.
Okay.
Perhaps it manifests itself somewhere else, or not in this training set at all, maybe in the future.
Okay.
Other questions? Okay, so let's move ahead. So the only thing that's left, in my opinion, actually no, the one thing that's left right now is the definition of best. So let's see what that is. And I'm going to skip, kind of rush through this example that we saw last lecture. Our goal is to pick a tree that is, to construct a tree that is as small as possible. But what does it mean to say that a tree is as small as possible? That's the smallest depth. And in fact, in your homework, you'll be playing with this idea of depth of trees quite a bit, because I'll ask you to construct trees of a certain depth. And you should try to think of how you would do that. I mean, you construct trees that are no more than a certain depth, actually. So even though if you run the tree, so that the only way, in some sense, what you have to do is short circuit this section here. If the depth is more than something, you just don't grow the tree anymore. But smaller trees have are better. Can anyone tell me? I'm going to make a statement, or I just did. I'm going to claim that smaller trees are better. Why? Can someone try to justify that claim?
Fast.
Yes.
Not like, just as a general rule, you have to deal with this is the simpler a solution is, the more likely it is that it's right.
Yeah, yes.
Search is complete.
The search is complete. The search could be complete with a larger tree as well. So you would, a larger tree will classify the data as well. Yes.
Isn't it just that there's less comparisons, so it gets done faster?
So there is this the speed aspect to it, the time complexity. But I'm going to argue time complexity is not that big a deal because we're talking about trees here. You just have to do a few more steps. It's a constant. I mean, once the training is done, you just, it's a constant. And as my colleague Suresh likes to say, what's a constant between friends? But I think the answer that you said is the one that I like the most, or at least the one that I feel is most aligned to what how I rationalize this. But there's another question or answer.
The smaller the tree, lesser the permutations and combinations of different versions of that tree.
There are fewer smaller trees. Now, if there are fewer smaller trees, that means, remember that learning is search over hypotheses. If there are fewer smaller trees, you're searching over a smaller space. And in some sense, you can think of the size of the tree as a surrogate for the complexity of its explanation. So you're explaining the data, the tree is explaining the data. The size of the tree or the depth of the tree is a surrogate for how complex is your explanation. And it's almost a philosophical point for now. We will make this point more concrete and formal later on in the semester, but for now, it's just a philosophical thing that says less complex explanations are better because they tend to generalize better. As an extreme example, in the tennis playing case, suppose I had a feature that said, what is the date today? Now, in some sense, the date is a perfectly explaining thing, perfect feature. On, what is the date today? September 1st, I play tennis. September 1st, 2016 will never happen again, but it explains the past perfectly. If that was the only feature. So, if I do that, then the tree is going to be massive. So, you're going to overfit by, by using an attribute that is irrelevant. So, anyway, the point is, we would like to construct trees that are as simple or as small as possible, but as much as we would like that, there's a theorem that says constructing the smallest, finding the smallest tree that's consistent with the data set is NP hard. So we can't do that, and ID3, the algorithm that we have, is a greedy heuristic. It does not go back and correct a mistake. Once it picks a root, it just keeps growing. It does not go back and say, you know what, maybe after like 3 steps, maybe I should go back and find a different route. No, it's a greedy heuristic for constructing a tree, and by choosing the definition of best carefully, we might be able to guide it towards smaller trees. That's the hope. Alright, so we saw this example. I'm not going to go over this. The point of this example here was that we need a way of identifying so let me go back here. We need a way of identifying that this situation here is better than this situation, because if you split on A, you have already decided on the label for a larger number of examples. Here 100 rather than 50. If you split on B, your uncertainty is still kept alive. So it's better to, if you care about building a smaller tree, you want to get to the leaf as soon as possible. The leaf corresponds to the label. So you want to decide a label as soon as possible. And one way of thinking about it is thinking about some notion of disorder in this that is introduced by, or that is removed by picking this label. So far, is this okay? Any questions so far? Okay. So let's start today's lecture. The point of the ID3 heuristic that was developed by Quinlan is that this is a problem of the insight that the ID3 heuristic brought into the world is that this is an information theory problem. We are talking about information. We are trying to quantify the uncertainty of information, and so we should use an information theoretic way of defining uncertainty. And Quinlan's algorithm, the ID3 algorithm, uses entropy. And we started on what is entropy. I'm going to give a quick sort of a crash course on what's entropy, and this is no substitute for actual reading about it. So I encourage you to, I think someone posted some notes on entropy on Canvas. There's actually a ton of material out there, and you can check it out. In some sense, you can think of entropy as a measure of surprise, a measure of impurity or disorder. So let me try to build this up from scratch. Suppose you have two events, plus and minus. And plus has a probability of p plus and minus has a probability of p minus. Now, if the event plus happened, let me try to ask you, in fact, let's say that p plus is 0.01 and this is 0.99. So it's a coin, let's say heads or tails, heads occurs with probability 0.01 and tails occurs with probability 0.99. And let's say I toss the coin once and it shows up a plus or heads. And I ask you, what is the information I have conveyed, or in a very loose sense, what is the surprise? You'd be surprised if the improbable event happens. In a very hand-wavy way, one could say that the surprise of an event should be somehow inversely correlated with the probability. Lower the probability, more surprise. And there is actually a way of deriving this from first principles. I'm not even going to attempt to do that. The information that is conveyed by choosing plus here is, or the information by picking plus is negative log p plus. This is inversely correlated to the plus. And the information that's picked by, or the surprise of minus is negative log p minus. And there are ways of deriving this from the first principles just using definitions. So entropy can be thought of as average surprise. So the probability that this would be the surprise is p plus. So the average surprise is p plus times minus log plus p minus times so the average information that is conveyed by this random variable is entropy. Yes?
Is this log to the base 2?
Yes. Typically it's log to the base 2.
Why is it?
It's a historical thing, the math works out better. In fact, the reason we call it a bit is it also comes from this thing. Log to the base 2 because a binary event has two probabilities and the maximum entropy here is 1 bit.
So in this example it's base 2.
Yeah, but the definition of entropy is always base 2. But if you think about it, it does not really matter. It's just scaling by a constant. So it doesn't really matter, but at least for our purposes it's irrelevant. But for all your homeworks and stuff, if you're wherever I ask you to tell me what the entropy or information is, use log base 2. Yes, I should probably say this is log to the base 2 somewhere in the slide.
For here, entropy is correlated with physics.
In fact, it's a generalization of the idea of thermodynamic entropy.
Okay.
It's actually mathematically, once you abstract it sufficiently, it's identical. This is about information, and once you abstract it to the level of probabilities, it's identical. Alright, so this idea can be generalized when you go beyond just two outcomes. If you have k outcomes, the entropy is just the same thing. It's the average surprise or average information. Okay? Alright, so just to illustrate this point, so the entropy will be the maximum when there is maximum uncertainty. And the maximum uncertainty happens when, in this case, p plus and p minus are identical. So you have no way of knowing what's the what the outcome of the coin will be. So the entropy will be, and in fact that is when I said there's a way of deriving the definition of entropy from first principles, this is an axiom that is used to derive it. The entropy should be maximum when the distribution over the outcomes is uniform. In this case, when p plus equals p minus equals half, you get, I'm going to just use this, minus half log half, that's for the p plus, minus half log, again log 2 to the base half, each of this is 1, and so the whole thing adds up to 1. So when you have two random variables, the maximum, or sorry, when you have two possible outcomes, the maximum value of entropy can be 1. Let's say when p plus is 1 and p minus is 0, which means I'm going to toss a coin, but I'm going to tell you that it's going to be heads every time. And I toss the coin and I tell you heads. Have I conveyed any information? So if p plus equals, so let's do the same thing again. If p plus equals 1, p minus equals 0, then the entropy is minus 1 times log 1 minus 0 log 0, and the assumption is 0 log, actually you can, as limit of, you use the limiting value there of 0 log 0, this becomes 0, and log 1 we know is 0, so the whole thing is 0. So there is no information that's conveyed. I personally like to think of the awesome example from an AI textbook. If I tell you that it's raining in Seattle, and you've been to Seattle, those of you who've been to Seattle, if I tell you it's raining in Seattle, I have given you no information. So I'm not much of a weather station if I predict that it's going to rain tomorrow in Seattle. Most likely it is. So the probability of rain is so high that it's okay. They have given you no information there, and the entropy of this rain or not rain random variable is rather low in Seattle. And in fact, interestingly, it's also rather low in Salt Lake City, because we are in a bit of a desert. So most likely it's not going to rain. So it does not, the other important thing to notice here is that it does not really matter what the actual semantics of these random variables are. All we care about are the probabilities. So this whole definition shows up with probabilities, and this also makes sense for the decision tree thing. I don't really care what the value of the feature is. We need a measure that is independent of the semantics of the domain. We need a way that is a way of constructing trees that is entirely dependent just on the statistics and not on whether this tree is going to be used for predicting the outcome of a baseball game or not. So more pictures. Blue bars here are the entropy, and if you have, this is the same thing that I mentioned. If you have a random, so these are actually probabilities, the black bars, and if you have if you have even or equal probabilities, then the entropy is high here. If you have somewhat unequal probabilities, the entropy gets lower, and if you have extreme, almost certainty, the entropy is very low on this side here. And this generalizes not just to two random variables, two outcomes, but to k outcomes. If you have, among these three, which of these three will have the highest entropy? The middle one, because the uncertainty is the maximum. So it will look something like this. And of course, these are cartoon pictures. The lens have no meaning. Are there any questions about entropy? Otherwise, we'll get back to decision trees. Yes.
So I know you just said the length's not meaning, but entropy max can't be over 1.
Entropy can be over 1. Can, because in fact, that's a good point. Let's take, this is the last exercise that I'm going to do with entropy. Let's say we have three outcomes, 0, 1 and 2, or let's say we have A, B, C. Say probability of A is 1/3, probability of B is 1/3, and probability of C is 1/3. Let's work out the entropy. The entropy is minus 1/3 times log 2 to the base 1/3 times 3 really, right? Because each of them is going to be the same thing. That is really log 2, log 3 to the base 2. Log 3 to the base 2, I don't know what the number is, but it's definitely more than 1 because log 2 to the base 2 is 1, which means log 3 to the base 2 should be more than 1. So entropy will be 1, the entropy is maximized to 1 only for, in the discrete case, only for binary cases, binary random variables. Yes?
Sorry, can you repeat why the negative sign?
Oh, I did not tell you why the negative sign, because what, think of it as a definition.
Yeah.
Yeah, for now just assume it's a definition. I really don't want to derive it. There is a set of axioms that you assume, and this is pretty much the only function that satisfies it. The axioms include things like the uniform distribution has the highest entropy, and entropy in the information should always be positive, and such things. And this will be the only function that satisfies it. If you want the hand-wavy version of it, I want you to think of, if you have a probability of an event is p, then the information is negative log p. This way it will be greater than 0, because log p is a number smaller than 1. Log p will be less than 0. Negative will make it positive. Yes?
So the entropy is highest at the root and then it reduces as we go down the tree?
That's the hope.
Okay.
That's the hope. In fact, I don't know of an answer to that question yet. It will be interesting to see what happens in practice. And it seems like that should be the hope.
Doesn't generalization decrease as we go down the tree then?
You are left with fewer and fewer smaller subsets of the data as you go down the tree. So, in fact, we won't be even using entropy directly. We'll be using a function that's based on entropy. So, that's a good question. Keep that in mind. I would like to try that out empirically. I have to think about this stuff. Alright, so going back to what we care about, we want to pick the root attribute, and we're going to use entropy inside our definition of to help us pick the root attribute. And the way we use entropy is to use something called the information gain. What we want is, we want uncertainty to go down as we go down the tree. And the way to think about this is, at the top, we are sitting at the top of a tree, say, and we have a data set S. And say I have picked an attribute A. At the root of the tree, the entropy is just S. So the tree looks like this. You have A, and then you have B1, B2, let's say we have 3 cases. Now, at the root of the tree, before we have done any splits, the uncertainty on that, at that level is the entropy. And we want to pick an attribute that reduces the uncertainty the most. So let's calculate the entropy for each of the subsets that we have here and average it out. So that is this term here. This is the average entropy of the thing on this box here denotes the average entropy of these 3 partitions. We have partitioned the data, we have some S here, and let's say this is SV1, SV2, and SV3. We have 3 partitions of the data, each of them have their own entropy. And we can always, so let's call this, the symbol H is used for entropy, so I'm going to use H of S here. So this has an entropy H of SV1, H of SV2, and suppose, and what is the average entropy of these partitions? It is simply the proportion of examples that go here, that is number of examples SV1 divided by the total number of examples plus each of these things. So the terms on the inside the box is the average entropy of the partitions. So we have the entropy at the root minus the average entropy of the partitions, and that is the uncertainty reduction that is given to us by picking this attribute A. Does it make sense? Does this seem intuitive? Notice, by the way, that this uses entropy. It could technically use any measure of disorder. There are other ways of measuring disorder. And another way of measuring disorder, for example, is called the Gini coefficient or the Gini measure. And you will be using the Gini measure in your homework in addition to this. There are other ways. In fact, Gini is used in the family of, a very popular family of decision tree algorithms called CART, classification and regression trees. Entropy was the first one that historically it was older. So, at some point I should learn how to right click properly. Alright, so another way of thinking about it is, if according to this, if you have a partition where most of the entropy is removed in one side and there is some entropy left, that will kill out one term, one of these terms, that will give you a 0 and the rest of the information entropy will be there. So this is going to be the way that we'll use to decide what's which attribute to split on. In other words, for every attribute that we have at this place, in this branch of the ID3 algorithm, we'll pick every attribute, calculate its information gain, and pick the attribute that has the highest information gain. As an exercise, I want you to go back and use the information gain to see which attribute A or B would have been chosen in the tiny toy example that we had earlier. And remember, you have to always think low entropy is low uncertainty, high entropy is high uncertainty, and what we want is to reduce entropy. So picking the attribute that reduces the entropy the most reduces uncertainty the most. Any questions about information gain? Hold on to your questions if you have any. We'll work out an example, and maybe that will resolve at least the mechanical aspects of this. So let's go back to this tennis example, and this was just to remind you, this is the data set where we want to decide whether we should play tennis or not, and the features are, the attributes are outlook, temperature, humidity, and wind. So let's first calculate the entropy of the data. I have 5 negatives. So the number of negatives is 5 and the number of positives is 9. So the probability of, if I think of this as probabilities, then the probability of the negative is 5/14th. So the entropy is simply this term here. I mean, I just worked through a few examples of this kind, and the number is whatever it is, I don't care. So our goal is now to iterate over each of these things and pick an attribute that gives us the maximum reduction in this entropy. So let's first work out the information gain for outlook. So we are looking at that column. For when outlook equals sunny, that's basically these 5 examples, the number of negatives in these 5 is 3 and the number of positives is 2. So the entropy for the sunny case is negative 2/5 log right, and that's that number there. I can do what I need to do to calculate the information gain is I need to do this for every possible value that this thing will take. So when outlook is overcast, notice that when outlook is overcast, you have this row here, you have this row here, and these two. It's always plus. So the entropy is 0. So when outlook is rainy, you get some entropy. So the expected entropy of that we get by partitioning the data according to outlook is there are 5 examples out of 14 that have the first one. There are 4 examples that have the second one, and there are 5 again with the third one. So the average is the expected entropy of these partitions. And the information gain is the original entropy minus the expected entropy. So far, so good. Any questions? Yes.
Did you say we're trying to get the smallest number when we get the one?
We want the one that has the highest information gain. Now we've just done this for Outlook. We need to do this for the other three and pick the one that has the highest information gain. Because we want to pick the one that has the maximum reduction in entropy. The maximum reduction in uncertainty. So we can do this again and again. You do this for humidity, you get the same process. I'm not, you should do this, go over this later on. We can calculate the information gain for humidity. We can do it for the other features. So now I've calculated the information gain for all 4 features, and I have to decide which feature removes maximum, the most uncertainty. It seems like Outlook is the one that works, and so we'll split on Outlook. What that means is all we have done now is, remember in the ID3 algorithm we had to decide, pick an attribute for the root. What we have done now is we have decided that the root of the tree should be Outlook. And now we are left with subsets of examples under each case. Let's do the easy case first. When Outlook is overcast, every example has the label yes. Which means, see, right, when Outlook is overcast, you have this one, this, and this. And we knew this because the entropy was 0. So we don't need to grow the tree anymore. This is the base case. Every example has the same label, so we just put a yes here. And in the other cases, we need to repeat the tree using the subsets of examples that we have under those cases. So we have to basically continue till we have exhausted all the examples in some sense. So the worked out example continues this process. It looks at the case when Outlook is sunny. So we have now a subset of the data. And we repeat the same process. Under this, which attribute do we pick? Again, first we need to calculate the entropy of this data, of the label. So that is the entropy of 2/5, 3/5. And find which of the remaining 3 attributes. So we've already used up Outlook. So we have 3 more attributes to worry about. Which of the remaining 3 attributes removes maximum uncertainty? And we pick one based on the highest information gain. It turns out here it's humidity, and you can do the same thing, you'll get a tree. Just to summarize in a slightly different way, the ID3 algorithm, what it does is, it first, given a collection of examples, it says, are all examples in this collection labeled the same? Do they all have the same class? If so, then you just create a leaf node with that label. Otherwise, you find the attribute that has the highest information gain. Here I called it xi, I think. And now for every value that this attribute can take, you create a branch for the tree, and you do a recursive, you recurse on that, for that attribute. So you have a subset of examples where that attribute takes the specified value, and you recurse using that subset. Yes?
Can you go back to the previous slide? So here, if you had decided on Outlook, and then say you are working on Sunny, and with the remaining examples you have on Sunny, you might decide the remaining 3 features in a specific order. But if you work with the same way on the other 2, overcast and rain, the features may not partition in the same order.
They will not. They need not. There's no reason that there's no reason that the different subtrees should be there's no reason for there's no symmetry requirement here. So I could have humidity here and something else here, because once you come down this path, you don't care about what's happening in the rest of the tree. That's why it's a greedy heuristic. Other questions? Yes?
As we're trying to maximize information gain, so are we choosing the attribute that has the lowest entropy?
No. We are choosing the attribute that has the lowest change in entropy. it turns out that this will be it will end up being that, because notice that this term here is a constant. To go all the way back. Notice that this term here is independent of A. So we are choosing the attribute that has the highest, the highest value of this thing, the average partition, the average entropy of partition.
But you're trying to maximize gain, right?
Yes, I'm trying to maximize gain. So I'm trying to maximize. Oh yeah, you're right. Yes, that's right. So we pick the one, in some sense exactly that. But this quantity is defined as the information gain. So if you ever are asked what is the information gain of something, it's not just the second term.
Okay.
But yes, you are right.
So in this definition we have a division term SV upon S, but during the example we did not find.
Of course we did, because there is
2 or 5.
here 5 over 14. Right, 14 is it's the average. Alright, so if there are no questions, yes, question.
So you told that your aim will be to minimize the entropy. So you should not subtract the maximum entropy thing from total entropy of the tree.
What is the maximum entropy here?
So like you are subtracting SV by S into entropy S0. So that's sort of entropy of A.
Yes, so that's the expected entropy of A.
Yeah. So you told that your aim will be to minimize the entropy of tree as we go down.
No, so I would like that to happen.
Yeah.
But I do not know how to do it computationally easily. So this is going to be a surrogate for that. We are not doing a formal actual minimization, but I think that's not your question.
My question is like you are decreasing, you told that you will be decreasing the entropy of a tree as, you aim to decrease the entropy of tree as you go down.
Yes.
So shouldn't you subtract the maximum thing?
What is the maximum of what? So in this example, we are, it turns
you
out
go back to the formula of gain.
Sure. Oh, no. This is not good. Okay, so. Right.
So from here you are subtracting the thing which has lower entropy, like A, considering A.
A is, what do you mean the lower entropy? So our goal eventually is to find some A, let's call it A star, the best attribute is max over A, something like this.
Yeah.
Yes.
So for that thing, you will be subtracting the attribute which is having lower entropy.
I'm not subtracting anything here.
From entropy is.
Yeah, yeah, right. So that's max A. The whatever. Yes.
Yeah. So that subtracting element shouldn't it be like?
Oh, you want to find instead of the sum here, you want to find the max.
Yeah.
No.
That doesn't work. So who can answer that quickly? You already spoken. I heard another voice here. You've spoken once, so.
I mean, this was my question as well. So, if you are trying to decrease entropy, should we go for should we subtract the attribute that has the maximum entropy?
So let's say that let's say we subtract the attribute that has the maximum entropy. Now, what will happen is that you will, notice that we are not caring about this V here is not an attribute, but the value that the attribute can take. So when you split on that attribute, you have to create one branch for every value that the attribute can take. So the summation is over all possible values that this attribute can take. So there's no point in finding an attribute that is perfect when there is so much noise. Let's pretend that we have a feature that splits the data into say 3 possible values, and one of them is clean, meaning the entropy is 0 there, like in this case that we had. Here, it's perfect, it gives you a perfect thing. But there are, suppose these other two were so large that it actually ruins the average case, the average situation. It's possible that by splitting on an attribute, you can get one branch that is clean and the other two that are so noisy that by making the split, we've actually lost more than we might have, than what we gain less than what we might have gained by picking something else that has a better, that is equally good across all branches.
They have another physics meaning about why this maximum is entropy for the system. If your entropy is maximum available, it will be stable. So the system will be stable. So that's why you choose.
Yeah, see, that's the thing. That's where I want you to remember that we are not explicitly the intuition is right, but we are not maximizing the entropy. We are hoping to maximize the entropy, but we are just doing this in a greedy way. There's no guarantee that this gives you the best tree. If there are questions, let's discuss this after class or something like that, because I do want to actually move ahead. So we've constructed this tree here, and so yeah, to answer the question that came up earlier, you can have a different splitting point at different subtrays. Alright, so let's talk about the hypothesis space. Let's go back, go up one level in our discussion, going back from the mechanics of the algorithm back to discussions about the space of functions. So our hypothesis space is a set of all trees. And I told you that in the last class that decision trees can represent any Boolean function, which means our hypothesis space is the search, in some sense, the hypothesis space that we are searching over is a set of all possible functions. Right? And I told you also, maybe last week, that if you search over all possible functions, we are in trouble because there are a super exponential number of functions. If you have n features, you have 2 power n functions. So something seems off. If the way to generalize is to restrict the hypothesis space, we've not done that here, because we are searching over an arbitrarily over every possible Boolean function or every possible discrete function. So I want you to keep that in mind. I mean, the decision tree algorithm is the learning algorithm, the ID3 algorithm will find you a decision tree that fits your data. If your data doesn't, even if your data has noise, your tree will fit the noise. So your tree will have noise because you are going to represent every row in the data as in the tree. So if you, in that sense, there's something to worry about when you're using the decision tree algorithm because you might end up overfitting. We'll talk about overfitting a lot. The other thing to remember is the minimum, we are only heuristically trying to find small trees. There's no guarantee that we'll find a small tree. This is a batch algorithm, by the way. A batch algorithm is a learning algorithm that makes decisions based on the entire data set. Very soon, maybe starting 2 weeks from now, we'll look at a family of algorithms that are called online, which takes one example, makes some decision, throws it away. It does not have to remember the entire data set. So we'll talk about the pros and cons of decision trees in a bit, but I want you to remember that it is not necessarily a good thing to represent every possible discrete function. So let's see where we are. We started this journey last week. We looked at what is a decision tree. It's just a decision tree is just a data structure, nothing more. It's just a data structure that can represent functions, discrete functions. In fact, it represents data because it's a data structure. It represents data sets. We looked at an algorithm for learning decision trees, the ID3 algorithm. It's just a very simple heuristic. There are way more complex functions out there or learning algorithms out there for decision trees. But the general theme of all of them is similar. And the algorithm in like 3 sentences, if all examples have the same label, then we are done. You create a leaf. Otherwise, you find the most informative attribute to split on, you split on that and you recurse. Alright. That's the, the clean version of the algorithm. Now let's get, machine learning is about real data, which means you're going to have to deal with all the dirty noise and stuff, dirty attributes that come with real data. So let's try to see what we can do with, look at a few tips and tricks for decision trees. There are variants of information gain that exist out there. Information gain is just one way of asking what is the best attribute. Another way of measuring a disorder is called majority error. And it says, if the tree, suppose I stop growing the tree at this point, I do not grow the tree anymore. I have a collection of examples, but I am forced to pick a label. What will the error of that label be? And I want to pick an attribute that gives me the minimum error. So, for example, suppose I have in some in a collection, I have 15 pluses and 5 minuses. And I decide that the error, the label for this collection, the entire collection is a plus. What will my error be? What's the error ratio? 1/4. And if I decide that the label is a minus, the error will be 3/4. So the majority error functions of, it looks a bit like entropy. It rewards picking. So here the majority error is 1/4. Similarly, if I have 15 pluses and 5 minuses, if I have 20 pluses and 0 minuses, what's the majority error? 0. So let's actually do a little bit of, if I have 20 pluses and 0 minuses, the majority error is 0. What's the entropy? 0. If I have 10 pluses and 10 minuses, what's the entropy? 1. And what's the majority error? Half. Which is the maximum it can be. Because if I have, 5 and 20, I get 1/4. So this has the same shape, in some sense, as a function, as entropy does. If I draw a graph of P plus and the entropy, it maximizes in the middle. This P plus can be between 0 and 1.
Is that last one 1/4 or 1/10?
Did I? Oh yes, you're right. I assume that the total. Yes, you're right. Good catch. So if I plot the entropy, it's going to be a function that looks like this. It maximizes in the middle at when it's half, and it goes down otherwise. It's a concave function. This kind of a function is called a concave function. The majority error is linear. It grows up and then goes down, and again it maximizes in the middle. So it has a similar sort of a bias, the inductive bias, as entropy does. And you can build a decision tree just by you can create a variant of the ID3 algorithm. Wherever you used entropy, you can use majority error. And there are other such functions. In your homework, you'll be using the Gini measure, which is another function that penalizes impurity. And you'll be using that in place of entropy and comparing to the vanilla ID3 algorithm versus the Gini version of it. Okay? Here's another interesting question. Suppose your data is not complete. Suppose, for example, for day 8 here, I forgot to take the reading of the humidity sensor, or the humidity sensor failed. I don't have that information. How do I deal with it? Yes?
You just just discard that whole?
That's one option. I can discard the whole thing. But say I want to use it. Can you come up with some ideas?
It's only an issue when you get to the point where humidity is a factor in the tree, so you can still use it.
Oh, but
that point.
even at the first step, I need to, I need to evaluate the quality of humidity, right? In order to evaluate the quality of humidity, I need the entropy of the label with respect to that split of the feature, that value. Yes?
Can you just decide which would be the highest probability humidity? So in this table time.
That's an option. I can just say that, I didn't see it, but just looking at it, it has been high most of the time. Most likely it should have been high. So let me just remove all the question marks and replace it with high. Yes?
Do kind of what he said, but give it like a random value proportional to the percentage.
That's a more sophisticated strategy. So here what you do is, out of the 4 values that are observed, 3 of them are high and 1 of them is normal. So what you do is, instead of giving a whole value here as high, you can say it is actually 3/4 high and 1/4 normal. Because is that going to hurt you? Eventually you're going to use these things only to count. You'll count how many highs and how many normals. So if I had replaced this with a high, I'll have 5 examples. No. I have 4 out of 5 high and 1 out of 5 normal. That was the first suggestion. I just picked the most frequent value and I replaced the thing. Instead of that, I could say, this is not a high or a normal, it's actually a mixed state. It's 3/4 high and 1/4 normal, which means when I'm counting, this whole thing fits in here, which means when I'm looking at the number of examples, when I'm doing my count, I'll have 3/4 high and 1/4 normal. That is my summary of this whole feature.
Is that over 5?
Basically trying to keep the
Oh.
expectation.
No, yeah, over 5, that's right.
So you're trying to keep the expectation of that particular value the same.
Yes. Yes. So that's another strategy. I mean, I'm not saying this is the only other strategy. Any other example, any other ways of doing this? You've spoken before. Someone who's not spoken.
Could you just insert 2 data pieces, one with that value high and one with that value low?
It's very similar to the other strategy,
Okay.
but then you're adding a little bit of extra information. You're saying that they are both equally probable.
Okay.
Whereas by doing this sort of a thing, this is like saying you've introduced 4 new examples, 3 of which are high and 1 of which is normal.
Okay.
But you're weighing those 4 examples. You're allowing those 4 examples only a weight, giving that only a weight of 1 because you're dividing by a fraction. You had a suggestion?
Yeah, try to find another example with the most similar.
Oh, that's very cool. Yeah, you could totally do that. Yes. One more and we'll move ahead. Someone here raised, yes.
We can try to fit a value that maximizes entropy. That will ensure that.
I don't know how that works. That's kind of, it seems circular. It seems circular enough and kind of tricky. I'm not sure. It might be correct. I can't tell of right now whether it's right or wrong. That's kind of, okay, yes.
Wouldn't you want to actually find an example that minimize entropy or minimize custom size?
Oh, so you want to find a label, a feature value that in some sense offers as little information as possible. That's probably not a bad idea. You want to find a feature value that does not add any information because you don't know what can be there. Okay, so all of you have a bunch of cool suggestions. Some things that are often seen in the wild are all of these suggestions involve completing the example. You have a question mark, you replace the question mark in some way or another and create a complete example. One of them is to find the most common value that this attribute takes in the entire data set. You could also, I'm surprised nobody gave me this suggestion, Instead of taking the most common value in the entire data set, you take the most common value among examples that have that label.
They did. Somebody did say that.
Somebody did? Okay, then somebody did. The other example is taking a fractional count. And I have often found that the fractional count example confuses people the most. So I encourage you to kind of stare at it later on, and if you have any questions, come back. In particular, I want you to think about how this will change probability calculation. Yes?
It just that I was thinking, if we don't want to add any information, could we just put 1/2 high and 1/2?
But half is adding information. By saying that it's half high and half low, you are saying that they are equal probable.
Yeah, it could go either way, so we don't add any information.
Yeah, but why half? Why not 3/5 and 2/5?
That would give some information.
But you.
I don't, doing it that way with the 3/5 and 2/5 or whatever wouldn't change it at all.
It wouldn't, doing 3/5 and 2/5 would not change the probabilities. But half and half, then actually, you're saying that in the absence of any information, both feature values are equally likely. But imagine again the example of Seattle and rain. Would you do half? If I tell you that in the last 100 days, it has rained 98 days, it was sunny one day, and one day I forgot to take a reading. Would you still do half? Right. Yes?
Why don't you take that example and testing data and classify whichever...
but you don't have, you can't see the test data.
Yeah, so classify using the data which you already have. Classify which attribute does it belong.
Oh, right. So that's actually, yeah. You can think of that attribute that's missing as if it were the true label.
Yes.
You build something like a decision tree, predict that attribute value, and then retrain the decision tree. Try it. No, I'm not saying it's a bad idea. Try it, seriously. What do you do at test time? Now let's say an example comes in, you've trained a tree, you have a tree, and then now you get a test example with some question mark there, where you're missing an attribute. What can you do? The same thing. Do the same thing again. Whatever you did during training, you do during testing. Alright. So, another question. We spoke about this briefly. What do you do if the features are not Boolean? So, we've already seen this. If your features can take multiple values, you just take as many splits as the number of values it takes. So, the outlook is not Boolean, it can take 3 values, you just do a multi-way split. Another way of doing this is to actually force it to be Boolean by converting this outlook is sunny to 3 attributes. So blue here is an attribute name, and what's in black here is the attribute value. So converting the fact that the outlook is sunny into 3 columns. So originally you might have had and the value here is sunny. Instead we convert it into 3 columns. Outlook, sunny, outlook, rain, and so on. And this gets a true, and this gets a false, and so on. So we can binarize multivariate data this way. Now, if you do this, what will happen is you will get trees that are very big, because now you have this extremely large number of attributes. Yes?
So why wouldn't you just make it one attribute, that outlook is sunny? And then it's true if it's sunny, and then it's false if it's
right. But then if for an example that has outlook rain, the outlook is rain, then you'll get a false here, but you have to encode that information somewhere else. Now, this might seem like a harebrained strategy. You're just creating a whole bunch of attributes, which means you're guaranteed to get a much bigger tree. I want you to keep this trick in mind, because it's a convenient trick for much later when we have algorithms that can deal with binary features. When we have algorithms that do not know how to handle categorical features, binarizing them is a very useful trick, especially when we come to things like classifiers like linear classifiers. where a linear classifier may not know how to deal with a discrete label like sunny, but we can always encode true as 1 and false as 0. So just a useful trick that you will see very often. So I just want you to know this. We saw this in the last lecture. What do you do with numeric features? You use thresholds or you use ranges and discretize them that way. Because remember, every node in the decision tree is a test. It has to have a finite number of branches going out, and if you have numbers, you cannot deal with it. So you need to discretize it somehow. Alright, let's get to the main point of the main thing that I want to get to, which is overfitting. Overfitting is the nuisance that we have to deal with in machine learning, no matter which algorithm you use. Overfitting is something that we will all do, both in machine learning and in life, and it's good to understand it intuitively and formally. So for now, let's get with an intuitive, get going with an intuitive definition. I'm going to define this function that I like to call the first bit function. The first bit function is a Boolean function with n inputs, and it just takes the n bits that are coming in and returns the first one. So the first bit function for 2 features is this thing here. You know, it sees true, false, 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 true, false, and so on. What this means is basically the features that come after the first one, after x0, all the other features are irrelevant. So first question, what's the decision tree for this function? Yes, it's a fairly small tree. Just split on x0. If x0 is false, you say false. If x0 is true, you say true. So you know that there exists a tiny decision tree. And also, on this data set, ID3 will generate this tree. And if you want an exercise to understand the ID3 algorithm, here's another example. Alright, so in the best case, suppose you have perfect data. Suppose you have all 2 power n examples. And you've trained a decision tree. Okay? Will there ever be errors in the future? Will your decision tree ever make mistakes? Why not?
Because the test data is included.
Yeah, but that doesn't. That is part of the answer. But that does not. There's another thing. That's the part that you mentioned before. But this is an important thing. The ID3 algorithm will build a consistent tree. It will build a tree that is consistent with the training data, which means it will be perfect on all training examples, and in particular, that one example that you care about, the test example. It's not just enough to have the test data in the training data, it's also important to say that the learning algorithm does something reasonable with it. Good. So, that's the easy case, and that's the situation that will never happen in real life. Namely, for 2 reasons. One, you will never ever see all possible examples, and you should be implicitly suspicious of clean data. I definitely am. I do not believe there exists clean data. So there will be noise in the data, and let's now introduce that aspect. Let's say we have noisy examples, but let's say examples. Let's say we have all 2 power n examples. This is, by the way, another first bit function. And let's say that we are now training trees, but the train and the test examples are randomly corrupted, only the labels. So what this means is the train and the test examples are no longer identical, and they might be randomly different. Is that clear? Okay. In this case, what happens is this is just some simulation that I ran some time back for different number of features. When you have 2 features and I randomly corrupt the train and test examples, I run ID3, I found the tree that on the noisy training set and I evaluated on the noisy test set. Obviously, I'm not going to get 100% accuracy on the noisy test set because I have fit noise, right? And you can, as the number of features keeps growing, the error seems to stabilize here in this case, but not always. It turns out that in the in the general case, the error stabilizes to this value. Yes.
So my question is, the data is corrupted or the test set is?
Everything's corrupted. Because that's going to be life. That's the way the things are. You have no guarantee that the data trained or the test examples are clean. Because they are all drawn from the same natural process. Right? So in this case, by the way, the error it seems converges to this value, and I encourage there is in the slides you will find a reason for analytically proving that it will converge to this value. It's just some a cute little puzzle, but that's not really the point here. The point here is that despite the fact that let's recollect what we know. If you are given a training set, the decision tree algorithm will find a tree that is consistent with the training set. If the training set has noise and the test set has noise, there is no hope that you will get zero test error. But what about the training error? In this case. Or the training accuracy. I'm hearing murmurs of an answer. So in fact, let me do something that, let me try to pick on a section of the class that I've not been hearing much of. You guys can't hear. Or anyone in this row. I usually, by the way, just FYI, I end up picking on the sides more than the front. So that will also encourage you to come to the front. Anyone? So let me try to recollect. The decision tree algorithm, we have noisy data, and the decision tree algorithm, the learner, will be consistent with the training set. So what's the training error? 0. Because it's going to be consistent with the training set. In fact, it will be consistent not just with the training set, but even with the noise in the training set. It will find some split that agrees with the noise. So the training accuracy is going to be 100% because the learning algorithm will find a tree that's consistent. Which should be an alarming situation for you because there's no way of knowing what's going on, what's the noise. The classifier is not perfect because of what is called overfitting. It not only fits the signal in the data, it also fits the noise in the data. It agrees not just with the signal that we want to capture, the first bit function that we have, but also with the noise in the data. Yes?
I'm just wondering, can the noise in the training data be inconsistent with the noise in the actual data?
So let me paraphrase your question so that everyone hears it. The question that was asked is it possible that the noise in the test set for a particular example, the label that the training set might have can be different from the label in the test set? In real life, it's entirely possible because every column here is a reading from some sensor, including the label. So there might be noise in measurement, there might be random perturbations that might just happen. It's possible that you might miss something, there might be noise in communication. So at every level there might be noise that is implicit in the problem itself.
So in that case, the results of the tree will probably not fit.
Yes. Oh no, it will fit the training set for sure. Because by construction, the ID3 algorithm by construction keeps growing a tree till every example is explained. Right? It will keep splitting.
Right. It will fit the examples of which the tree was built, but it will not fit the noise for test data.
Yes. It will not fit the noise in the test data. In fact, it might even introduce noise while predicting on the test set because it's too close or too biased by the noise in the training set. And this situation is called overfitting. So let me try to give a definition. As I said, the overfitting is a situation when noise is, the classifier explains the noise in the training set. Yes.
Can the noise result in some contradiction the examples saying that?
Most definitely it can.
So we have two exact same examples with the
Different labels. Possibly.
So in that case, can we still have
The-
this
the
zero error for the training?
The hope is that, yeah, right. If the training data itself has inconsistencies of this kind, then we can't get zero error. Yes, we are assuming that the training data does not have that two examples that are identical in the features but have different labels. That's an assumption that we have. Yes, good question. So, one way of defining overfitting is the following. We assume that the data, when I say data, both the features and the labels, and as I said earlier, I'll use the symbol X consistently to denote features and Y to denote labels. So we have some unknown probability distribution D over these rows. Okay, and the examples are picked from that probability distribution. And there is this hypothesis space H, and we are trying to construct classifiers from this. The training error of the hypothesis of a hypothesis, a function, is the error that function has on the training set. The decision tree case, for example, the training error is 0. The true error is actually the expected error that you get by drawing random examples from the true distribution and making a prediction. So it's expectation. This is interesting. This is the expected error of expected value of this thing. The expectation, and the expectation is over the training, over the true distribution. And what we call overfitting is, if there is, suppose our learning algorithm has picked a hypothesis H. It believes that this is the best I can do. The situation that overfitting is the following situation. There is another function in our hypothesis space, H prime, that has a higher training error, but a lower generalization error. So the true error is also called the generalization error. It may have a higher error on the training set, but overall it performs better on future. This is called overfitting. And this is something that we will strive to avoid in general. Okay? Questions? Yes.
So if the amount of overfitting predetermined by the algorithm, how could you do a pre-processing step?
No, it's impossible to know what the actual amount of overfitting is, because we never have the true error. The true error is on every possible example that is drawn from this distribution, so we never have access to that. So it is neither predetermined by, it is actually influenced by the training algorithm. We can change our training strategy to reduce overfitting, but there we have to introduce other kinds of inductive bias or learning bias. We change our learning strategy so that we reduce overfitting, but we cannot guarantee it because that's such is life.
So can you at least use the test data to predict your error?
We can use test data to evaluate the hypothesis, and in fact, we will use test data as a surrogate for this quantity. So another way of thinking of overfitting is if the training error is less than the test error. If the training error of the alternate hypothesis is higher, but its test error is lower, and the test error is a surrogate for the true error, which is why you should never use the test data for training. Last question, and we'll probably stop after that.
What if you do validation scheme on the decision tree?
That's what we have to do, in fact.
So if you do construct these kind of things, and then try to merge those things.
We will be using cross-validation quite a bit. In fact, that's the one right way of avoiding overfitting. And in fact, not when I say we, I mean you will be using cross-validation in your homework. And there's a long description of what cross-validation is. Alright, let's pick up from here on Thursday. And for those of you who came late, quick reminder, there's a homework that's on the class website. I strongly encourage that you start early.
Thank you.